right, here's your second screencast for the atomic structure unit, periodic table unit that we're going through. Today we're primarily going to focus on atom models over time. So that's going to be your notes title. The essential question for today is, how has the model of the atom changed over time? So you're going to see from, going from Dalton's atomic theory all the way through to the wave mechanical model, the quantum mechanical model that we use today. So we're just going to go ahead and get started with Dalton's atomic theory. So this is the development of atomic theory. How has our atom changed over time? So it's going to start with Dalton's atomic theory, the first experimentally based theory of atomic structure. There have been theories beforehand, before this, but they were not experimentally based or scientifically tested. So this is kind of where we start off with. Dalton actually had 6 parts to his atomic theory. Now today there are a few of them that we have proved false, but for the most part there are 6 parts to his atomic theory. The first one is all matter consists of tiny particles called atoms. He actually called them indivisible particles, meaning that they couldn't be broken down any further, and today we know that they can be. So that's this ties into number 2. An atom cannot be created, divided, destroyed, or converted to any other type of atom. Well, we know that an atom cannot be created. Really, an atom cannot be destroyed, but you can divide atoms through nuclear division, so we can divide the nucleus up. Dalton didn't know that the nucleus existed. He didn't even know that there were protons, neutrons, and electrons. So, and then it is true that we can't convert any other type of atom to any other type of atom. You can't make gold. You can do some conversions during nuclear reactions, but it's not like you can control what they become. They go through kind of a set pattern of decay, and so you just can't turn something into gold or turn something into carbon because you want to. And number 3, atoms of a particular element have identical properties. So that means that all of the atoms of hydrogen are going to behave like hydrogen. All the atoms of helium are going to have the properties of helium. All the atoms of carbon have the same properties of carbon. It doesn't matter which isotope they are, like carbon-12, carbon-14, they all behave the same way because they're all carbon. Number 4, atoms of different elements have different properties. Well, that would make sense. So each of the elements listed on the periodic table is going to have its own chemical and physical properties. Atoms of different elements combine in simple whole number ratios to produce compounds. That's how we make formulas. You notice that they are whole number ratios. We never have halves or quarters, or we don't use decimals. It's always 1 atom of this combines with 1 atom of this, or 1 atom of this combines with 2 atoms of this. So you end up with simple whole number ratios. And chemical changes involves joining, separating, or rearranging of atoms. When we do any type of chemical reaction, we're actually not changing anything about the atom. All we're doing is joining them together, splitting them apart, or rearranging those atoms in a new way to form just like a little bit of a different shape. It's really just interactions of the electrons. So from Dalton, we start to discover that, yes, here's the basic structure of an atom. Now, what's inside of this atom? And that's where you start seeing some work done with the electrons and then the protons and then the neutrons. So the electrons were the first subatomic particle to be discovered using a cathode ray tube. Cathode ray tubes are how old school tube TVs used to work. There would be a blast of electrons through a tube, that's why it's called that, and it would be magnetized. There would be a positive side and a negative side, just like this is showing right here. There's a positive side and a negative side, and those electrons could then be, or whatever, the current would then be moved or bent to make a picture or an image show up on the screen. Well, that is a cathode ray tube, and the current is the electrons, and you can control those electrons with a magnetic field. So that is how electrons were discovered, was using cathode ray tubes. The evidence for protons and neutrons came later. Protons were actually discovered by Goldstein, and they are the same size in charge, but opposite in spin. So even though we say that the proton is 1,837 times heavier than an electron, we do say that they have the same size charge. A proton counts as 1, an electron counts as -1. Neutrons were discovered in 1932. They were kind of predicted to exist in the 1920s, but it wasn't demonstrated, or they weren't proven to exist until 1932, so not even 100 years ago. And they were found to have almost the same mass as protons. The reason that it took so long to identify a neutron is because it does have a neutral charge. They knew there was something else inside the nucleus because the masses weren't adding up. It wasn't just protons alone, but they had a hard time finding it because they were neutral in charge, so 0 charge. So with the discovery of the neutrons, the discovery of protons, and the discovery of the electrons, really then came that, well, where are all of these things inside of an atom? Are they all just clumped together? Are the protons, the neutrons, and electrons clumped together in a plum pudding model, like Thomson's plum pudding model? And I can draw pictures of that for you in class. Or is there a designated region for each of these things? Well, Ernest Rutherford did what's called a gold foil experiment, where he took a thin piece of gold foil, so a few atoms thick. So here it is, just a couple of atoms thick. And he shot alpha particles at it. So he used this alpha particle emitter, which are the radioactive alpha particles. They are positively charged. So what he did was he shot these positive alpha particles through this gold foil. And he saw that most of the particles went straight through. They didn't hit anything. They didn't come in contact anything. So that told him this first conclusion, that most of the atom is empty space, if most of them went straight through. Well, they knew in that time that positive and positive would repel each other, negative and negative would repel each other, positive and negative would attract. So he concluded that most of the atom is empty space because it didn't affect the path of the positive alpha particles at all. But you'll notice that some of these alpha particles, it's like they came close to something and they got bent. So like this one gets bent at an angle. So they got what's called deflected at angles. And because they got deflected, that told him that something had to be there. And that something that was there was a positively charged, because positive and positive would repel. So it would push them off. And so that's how he discovered that the nucleus was positively charged. Now, the majority of the mass is located in this small, dense region. How did he discover that it was small and dense? Because a handful of those alpha particles would actually hit this and then bounce off. So you can see over here it's showing them reflecting back. Well, it has to be pretty gosh darn dense for something to reflect back. So he was able to conclude that most of the atom is empty space. The positive particles within that nucleus interacted with the positive alpha particles and deflected them, and then some of them reflected back because of that small dense region. So here's a diagram showing you the difference between Thomson's model and what Rutherford then discovered. Thomson honestly thought that there was just this like blob material that was positively charged, that there wasn't like a definitive particle that was positively charged. It was just all the space was positively charged. And the electrons were these little negative particles that were inside of it, spread out in no real order. This is called the plum pudding model because it looks like pudding with little plums in it. When Rutherford came along and did his experiment, he actually proved that most of the atom is empty space, and that's where the electrons reside. Now, you might be asking yourself, if the electrons are there, why didn't they interact with the alpha particles? It's because they're so small. This was more justification for how small those electrons are. They were deemed to be too small to actually affect the positive alpha charges. So even though they're there, they really didn't learn much about where they are. But they did learn about the nucleus, that the positively charged area is just this little dense region called the nucleus. So going from Thomson to Rutherford, there's a little bit more refinement to the model. Now Rutherford's atom was tiny, dense, positively charged nucleus of protons surrounded by the electrons. Now the question becomes, well, where the heck are those electrons? And that's where the Bohr model comes in at. Bohr uses the measurement of particle energy rather than position. So the energy that those electrons have. The electrons that are closer to the nucleus in those orbitals do not have as much energy as the ones that are further out. So that's why you see it in rings. Spectroscopy is the study of information obtained from the absorption or emission of light by atoms. The cool thing about atoms and these electrons is you can excite these electrons by giving them energy. So whether it be high temperature or electricity, you can give them energy and you can actually get them to shoot out to higher energy levels. When they do that, they have to come back down to their ground state, to their original state. So when they fall back down, they give off light. Well, how far they fall back down is directly proportional to how many layers or how many orbitals there are in that atom. So you can look at the light that comes out, the frequency of light that comes out of that atom, and be able to tell how far that electron moved. It's actually pretty cool, and that gave them the structure of an atom. So we have to know a little bit about electromagnetic radiation. That light is going to travel in waves from a source. We call electromagnetic radiation light because all we can see of it is visible light, but there are all sorts of different types of electromagnetic radiation that we don't see, like ultraviolet and microwaves and radio waves. Those are all light. You're just not able to see them. The speed of light is 3.0 times 10 to the 8th meters per second, so that's how fast that light is traveling. All the light sources travel at that speed. And you can use the light that's coming off of the atom to tell where those electrons were. So I'll give you a really awesome drawing of this in class. So a little bit more about wavelengths and waves. Light is propagated, or it moves, as a collection of sin waves. There's different types of waves, and light moves in these wave patterns, wave formats. And how spread out the wavelength is, and how fast it travels, or how many of these wavelengths pass a point per second, so what the frequency is, determines the color that you see light as. So wavelength is the distance between two identical points on successive waves. So from two tops or two bottoms or two middles, that's going to be the wavelength. And each wavelength travels at the same velocity, but it has its own characteristic energy with it. So even though the wave is traveling at the same speed, the speed of light, it does have how close or how far apart those wavelengths are. So these are further apart, so they would have a longer wavelength or a longer frequency. These are closer together, so they're going to have a shorter frequency. Here's the electromagnetic spectrum. And we associate frequency with being energy. So things that have a shorter wavelength are going to have a much higher frequency, so they're going to have more energy with them, like gamma rays, X-rays, and ultraviolet rays. These would be closer together on that chart, on a wave diagram. Down here on this end, these are going to be further apart. So the waves are going to be much wider. So a longer wavelength, a much lower frequency, so we consider that to be low energy. This is the stuff that's not dangerous. This is the stuff that is dangerous. So the higher energy, the more dangerous it is. And what we can see is just this little itty bitty teeny tiny bit of red light, or of visible light. So the red, orange, yellow, green, blue, indigo, violet, rainbow is the part of the electromagnetic spectrum that we can see. So how does this relate to the Bohr atom? Well, as I was saying earlier, atoms can absorb and emit energy via the promotion of electrons to a higher energy level and the relaxation to lower levels. All that means is the energy, or the electrons, are going to be boosted to higher levels out, and then they fall back down. Energy that is emitted upon relaxation is observed as a single wavelength of light, and that creates what's called a spectral line. Those spectral lines are a result of the electron transitions between the allowed levels of an atom. So as that electron moves, you get different types of light that are coming off. And I'm going to show you an example of this in class. So here's a spectral line for some different elements. So here's the spectral line for sodium. Here's the whole visible spectrum. Helium has its own spectral lines. Hydrogen has its own. So the emission spectrum of hydrogen led to the modern understanding of the atom. So here's a model of the Bohr atom showing the different energy levels, and I'm going to give you a better diagram of this in class tomorrow. We're going to go through quantization, when we say it gets quantized, excited, and relaxed.